All right, let's learn how to solve some decoupled systems of differential equations today. This is section 2.4. So in the last section, we learned how to solve the damped harmonic oscillator problem, which was also a system, but we were able to find a solution without kind of thinking about it via a systematic way. So today we're going to look at other kinds of systems that can also be solved if you look at them the right way. These are very special kinds. They're called decoupled and partially decoupled systems. And we'll be able to check our answers using differentiation. We'll also be able to use the HPG system solver program to look at solutions visually. We're going to be thinking of systems via vectors as well. So let's just take a particular system of differential equations here. So we've got an x prime and a y prime, so that's a system. The x prime is supposed to equal 2x plus y squared. The y prime is supposed to equal negative y. And you might wonder, well, how would you solve a system of differential equations that looks like that? You can recast it as a vector problem. If you treat x and y as maybe the position and velocity or whatever, you can treat them as a vector, call it vector y. And then the right-hand side, you can think of that as a vector field, right? It's a vector. It depends on x and y. So for every x and y, we get a vector. So this is a vector field. So we could call that the vector field f. And so you can write this system of differential equations as a vector differential equation. The change in state is given by some vector field based on the current state. And it will be helpful to think of it this way when we want to think about it geometrically when we're looking at answers. All right, so let's dive right in. Let's see if we can figure out how to solve this differential equation right here. One way is just let's try guessing some solutions. Okay, so here we go. Here's some, e to the t sounds good. Let's put down a bunch of e to the t's, and let's see if this is a solution to this differential equation system. Okay? Okay, so what would it mean for this to be a solution to this system? Well, y is equal to 2e to the negative t. That derivative better equal negative y. And x is equal to this. That derivative better equal 2 times x plus y squared. And so we can take the derivatives of these two functions and write them here. And then we can take these two functions and substitute them in. And then we can compare. And if they're all equal, then it's a solution. And if they're not equal, then it's not. So let's try it. Okay, so here's x and y, just copied over. The first question, I'll do the easy one first. Is y prime equal to negative y? Well, what's y prime? That's the derivative of 2e to the minus t. That derivative will be minus 2e to the minus t, like so. What's negative y? Well, that's just negative 2e to the minus t. Let's just write that down. And are those two things equal? Yes, they are. So that checks out. Good. Exactly what I wanted. Now let's look at x. What's the derivative of x? Well, that's the derivative of this, which should be e to the t, and then a minus 2 will come down, so that makes plus 2e to the minus 2t. So there's x prime. On the other hand, x prime is supposed to equal twice x plus y squared. So twice x is 2 times x, here's x, plus y, there's y, squared. And if we multiply that out, we'll get 2e to the t here, and we'll get a minus 2e to the minus 2t here. And when we square y, we'll get 2 squared is 4, and an e to the minus t squared, that's e to the minus t times e to the minus t, which is e to the minus 2t. So we get 4e to the minus 2t's. And we can collect these together. We have 4 and a negative 2, so that makes 2e to the minus 2t's, and we've got the 2e to the t. And does that equal e to the t plus 2e to the minus 2t? Well, not quite. We're off by an e to the t. That's a bummer. So that's not true. So this is not a solution. It doesn't solve the system because it doesn't solve both of them simultaneously. And so if guessing random e to the t's doesn't work, maybe there's some systematic way of actually working this out. So let's see. All right, let's start with an easier problem first, and then we'll come back to that one in a minute. So if a system is completely decoupled, and what I mean by that is look at the derivative of the x here. There's only x's. And look at the derivative of the y. There's only y's. So the x's are by themselves, and the y's are by themselves. they're decoupled from one another. There's no connection between the two. For all the x and y knows, this is one problem dealing with one kind of thing, and this is a different problem in another country dealing with a completely different thing, and there's no connection between the two. And that means we can just solve this one by himself and solve this one by herself, and now we've got a solution to the system just by solving the system separately. So can we do that? Sure. What's x prime equals 2x? Well, that solution is just c e to the 2t. We've solved that 100 times. And what's y prime equals minus 3y? Well, that's just y equals c to the minus 3t. We've solved that 100 times. And now you might be tempted to just put c on both of these, but the constant here doesn't have to equal the constant here. They could be different constants. And so we put c1 and c2 to indicate that they don't have to be the same thing. And what happens to an e to the 2t over time? Well, that's going to be exponential growth. Going up if c is positive, I guess it could go down to negative infinity if c were negative. And this is exponential decay. This is going to approach 0 no matter what. It could approach 0 from above or below. But in this case, I've drawn the x going up to infinity and the y going down to 0. So if I draw that in the phase plane here, the x's should be increasing and the y's should be decreasing, and so that means y's are going down and x's are moving to the right. And so plotted together in the vector field, it's going to look like this. At least this solution will. But if I had started with a different initial condition, it might look like this. And here's a bunch of them. So if I put that system into HPG solver, here's one that goes down and to the right. This one goes up and to the right. Again, the x's are increasing, but the y's are approaching 0. So if you start negative, they just approach 0 from below. If x is negative, it just goes to negative infinity. Y goes to 0 regardless. And you can see that in the x either goes up to infinity or x goes down to negative infinity. And y either goes down to 0 or it goes up to 0. And so this direction field here is telling you, again, the direction field should be 2x and negative 3y. So if we come back and look at it, when x is positive, the bigger x is, the farther it goes to the right. And negative 3y, when the y's are positive, these should be in negative. So the y, when you're here at positive, positive, we should have arrows that go this way because the y should be a negative slope and the x should be a positive slope. But when the x's are negative, then these arrows point backwards. And so you could graph that direction field, and that would sort of tell you the solution kind of follows the arrows in this direction field. All right, now we're back to that problem we had a minute ago that we couldn't solve by guessing, and so let's see if there's a more systematic way. Is this decoupled? Well, not really, because there's x's and y's in the x equation. However, in the y equation, there's only y's, and so we call this partially decoupled. It's not entirely decoupled. There's still a connection, but the y's are separate. And so what we can do is we can solve the y equation first, get the answer to y. Once we know what y is, we can plug it in for y squared here, and now it's just a function of t, and this is now an inhomogeneous linear differential equation, which we can solve using the method of integrating factors. And so this will get some good practice. If you were a little rusty on the integrating factors, you'll get some good practice during this homework assignment. All right, so let's try this. All right, so I'm going to look at the y prime equals negative y first. So let's solve that. Well, that's easy. Actually, it's just y equals constant e to the minus t. So that's done. And what's y squared? Well, y squared is just going to be constant e to the minus t squared. We're going to get that same constant squared, and then e to the minus t is e to the minus 2t. So this is what y squared is. And if I take that and substitute it in here, I get x prime equals 2x c1 squared e to the minus 2t. One thing you want to be careful of is this c1 and this c1 are the same c1. It has to be y squared. So whatever this value is, this has to be that number squared. And so I'm keeping that as a c1 squared. We can't write this as a new random constant because it's not random. These numbers are connected. All right, so now I've got an equation with just x's and t's. That's a linear differential equation. It's inhomogeneous, but that's fine. I'll use my integrating factors on it. Subtract 2x to the other side. What is the integrating factor? Well, it's a minus 2. So if I integrate minus 2, I get minus 2t. So it's e to the minus 2t. Let me multiply that here, here, and here. When I multiply e to the minus 2t by another e to the minus 2t, I, of course, get e to the minus 4t. And I keep the c1 squared there. So now this is written as a total derivative, right? This is fg prime plus f prime g. So when you integrate a product rule, you just get the product, and that's going to be fg. So fg is e to the minus 2t times x. On the other side, I integrate this. Well, this is just a nice function of t, so my antiderivative will just be e to the minus 4t over minus 4. That's the antiderivative, and the constant just comes along for the ride. But I also get a constant of integration. That's my c2 here. All right, so now I want x by itself, but it's multiplied by this integrating factor, e to the minus 2t. So I'm going to multiply both sides of the equation by e to the 2t, which will cancel this. When I multiply this by e to the 2t, I get c2 e to the 2t. And when I multiply e to the minus 4t times e to the 2t, I get e to the minus 2t. Now I want you to notice, before we move on, one thing that's interesting to see. We could have tried to solve this using a guessing method with the homogeneous and the particular solution. And if we cover up the y squared here, and we just look at x prime equals 2x, the homogeneous problem would have a solution of e to the 2t. And that's right here. There's your c2 e to the 2t. There's your homogeneous solution. And this particular solution, c1 squared over minus 4 e to the minus 2t, that must solve this equation, the entire inhomogeneous equation. And it does make sense, because if you guess something that looks like an e to the minus 2t, we do get something that looks like an e to the minus 2t. It just happens to have to be that divided by 4, minus 4. All right, let's stack them up. There's your x, there's your y. That's the solution. C1 can be anything, and C1 squared will just be whatever that is squared, and C2 can be anything. So we still have two things that we can determine, so we should be able to solve an initial value problem. The other thing you might notice is what's going to happen over time. Well, this is an e to the minus t, so this y should be shrinking to 0. This is an e to the minus 2t, so this should be shrinking to 0 as well. But this is an e to the 2t, so this should be going up to infinity. So my solution should either be going to the right or to the left, one way or another. And let's check that. So here we go. Can we solve the initial value problem? X is supposed to be 3 when t is 0, and y is supposed to be 2 when t is 0. Let's start with a y. That's easier. We plug in 0 for t. We get c1 e to the 0, which is, of course, 1. So c1 is supposed to be 2, so that's what c1 is. Now that we know what c1 is, we can put it in right here. 2 squared is going to be 4. 4 over minus 4 will be minus 1. If we plug in 0, we'll get e to the 0 and e to the 0. So we're just going to get 4 over minus 4 times 1 plus c2 times 1. That means that 3 should equal minus 1 plus c2, and so c2 should be 4. And now you've got a solution to the system, to the initial value problem. We can graph that solution using HPG solver. You'll see here solutions do in fact go down and to the right, or up and to the right, or down and to the right, or up and to the right. Or sorry, to the left, I mean. The x's are either going to negative infinity or to positive infinity. The y's are shrinking to 0 one way or another. This differential equation has this y squared, this non-linear term in it. And that gives us some of this interesting dynamics when y is close to 0. We see that it's not just that it's staying in the 4 quadrants like some of the other ones have. We can get some crossover in an interesting way here. We haven't really seen anything like that before. If you do look at just the y by itself, you'll see it does shrink to 0. And the x either goes up to positive infinity or down to negative infinity, just like we expected. If you want to play with the HPG solver, if you just put this in and put that in, you can see the vector field there, or the direction field rather. And we can start at 3, 2, and hit the solution. And that would be the one that we solve for. The y shrinks down, the x blows up, and it goes off that way. There's some fun, kind of interesting dynamics kind of in here, where there's, you know, the difference between going off to the right and going off to the left is, you know, is kind of an interesting thing. These two things are starting really close, and they end up having separate behaviors. And that's because of this y squared right here. It adds for some chaos in the system. All right, so what I want you to do is try this practice problem. You can pause the video and try to solve it by yourself, and then I will come back in a minute and go over the solution so you can check. So can you solve x double prime plus 2x prime equals 0? What you want to do is rewrite it as a vector system using x and v. Solve it. It should be partially decoupled, so you should be able to solve it by solving either x or v first. And then we can talk about what's going on and what would this model mean. All right, so hopefully you paused the video and you tried to figure out this differential equation here. Let's do it together now. So the first thing I did was I set x prime equal to v. What's v prime? Well, v prime is the same as x double prime, and if I subtract this over to the other side, that's minus 2x prime. But of course, x prime is v, so that's just minus 2v. So my partially decoupled system, you'll notice the v prime only has v's in it. The x prime has x's and v's, so we'll have to do that second. V prime equals minus 2v is easily solved. That's just c1 e to the minus 2t. And so if I take that, that's v. I can put it right here for v and solve x prime equals c1 e to the minus 2t. Well, that's easy enough to do. It's just a function of t, so I can integrate both sides. I get x on the left, and I get c1 e to the minus 2t over minus 2 plus the constant of integration. And so now I can write that down here. There's my x, there's my v. That's a vector. And you might wonder, well, what does this look like in the phase plane? Well, let's think about it. Let's look at the v first here. So this is x and this is v. This is a negative exponential. It should be shrinking to 0. So if I start here, it should be moving down towards 0 in the v direction. The x direction, well, there's some constant here that's not changing. And then we have this number, which could be negative, times an e to the minus 2t. So if c is positive, then c over negative 2 is negative. And so the negative part is shrinking, and this is remaining positive. So that's actually meaning that we're going to move to the right as the amount that we're subtracting off gets less and less and less. And so the x is actually increasing. And that makes sense because x prime is equal to v. If v is positive, I should be moving to the right. And in fact, I am moving to the right. And I'll approach, when these are both 0, I'll be at c2 comma 0. So this is what I would expect if I started here. And if we bring in the HPG solver, let's just change this. X prime equals y. Y prime equals negative 2 times y. And in fact, if I start there, I move down. What would happen if I would start down here? Well, in that case, the v would be negative. So x prime should be negative, so that means I should be moving to the left. The y should always shrink to 0, so now I'm moving to the left and closer to 0. Over here, the v is positive, so x prime should be positive, so I should be moving to the right. If I start down here, I should be moving to the left, and the v will always go to 0. Now, one thing that's really odd about this is these are all straight lines. Let's start at the point 0, 4 and see what happens. So that's right here. There's 0, 4, and it comes down and it hits. And where does it hit? It looks to me, the x is 2 and the y is 0. So that means the slope of this line, if I started at 4 and ended at 2, this is sort of down 4 over 2. That's a slope of like negative 2, basically. And does that actually make sense? Well, this e to the minus 2t and this e to the minus 2t, they're the same. So the amount at which x decreases is the same per unit time as the amount y decreases, except it's actually cut in half. So if y changes by 2, x will change by 1. But it will go in the opposite direction. So if y shrinks, x will increase, but by half as much. And that makes sense. If I started at 4, 2, if the y decreased by 4, the x should increase by 2. And that's exactly what we have right here. And so you can see that in the solution because the exponentials were the same size. And that's why these are all lines that shrink towards the x-axis. All right, that's all I have. So your homework is these problems here. You should get a lot of good integrating factor review in, a lot of good solving differential equations, playing around with HPG solver to check your answers, and solving equations.